Welcome to this explainer. Today, we're essentially turning into industrial detectives. We're going to investigate a totally hidden world, looking at exactly how everyday materials, everything from the airplanes we fly in to the bridges we drive across, are evaluated and kept safe for public use. And the crazy part? They do this without ever having to break them apart. To catch a culprit, and in our case that culprit is a microscopic material defect, we first have to intimately understand our suspects. Just look at this quote. It brilliantly illustrates that every single detail about a part, from how it was manufactured, to its size, to how it's actually used in the real world, absolutely dictates how we hunt down its flaws.
So here is our investigator's playbook for today. First, the industrial detective. Second, inside solid materials. Third, investigating casting defects. Fourth, pushing materials to failure. And finally, choosing your NDT weapon. Let's get into it. Starting off with Section 1, the industrial detective. You can really think of non-destructive testing, or NDT for short, as a highly advanced medical checkup, but for machines. The absolute key phrase in this definition is without adversely affecting the material. NDT allows us to examine a working part for hidden, potentially catastrophic flaws, while leaving that part completely intact and ready for future use. It's all about finding the problem before the problem finds us. Moving right along to Section 2, inside solid materials. Look at the stark visual contrast between these two states of solid matter. You've got the highly organized, grid-like atomic structure of a crystalline solid on one hand, and then, completely different, the amorphous solid, which is basically a tangled, chaotic, and random web. Honestly, recognizing these structures on a microscopic level is step one in understanding exactly how a material is going to behave under stress. Now, NDT is mostly dealing with solid materials, things like metals, composites, plastics, and ceramics. And because the atoms in these solids are tightly packed into fixed positions, NDT technicians can actually use specific testing methods to interact directly with those structures. By sending energy into those tightly bound atoms, they reveal structural secrets and assess the integrity that's hidden safely beneath the surface. Up next, Section 3. Investigating casting defects. Welcome to the Rogues Gallery. Our first culprit is a shrinkage cavity found here on an aluminum casting. When excessive shrinkage porosity happens during the cooling phase, it literally pulls the metal inward. It leaves this very noticeable physical depression right on the surface, so it's a glaring visual clue that the internal structure is compromised. And this perfectly illustrates hot tears, which are these jagged, intergranular cracks. Sometimes they sit right on the surface, which you can see clearly in a standard visible inspection. But a lot of times, they hide just beneath the surface. To catch those hidden ones, inspectors use subsurface techniques, like fluorescent liquid penetrant testing. Check out that vibrant green glow. That liquid actually seeps into the microscopic cracks and lights up under special lighting. It literally makes the invisible visible. Now, sometimes the problem isn't cooling too slowly, it's pouring too fast. When molten metal is poured really rapidly, it creates turbulent splashing. These little rogue droplets, they're called cold shots, solidify way too quickly. They fail to bond with the rest of the casting, so they act almost like unwanted hitchhikers just stuck to the outside of the part. Very similar to cold shots, we have cold shuts. In complex molds, manufacturers often pour metal from two different channels to distribute it evenly. But if those two streams of liquid metal meet when they're too cold, or maybe they've oxidized, they just bounce off each other instead of actually fusing together. This creates a massive, completely hidden separation point that severely weakens the entire structure of the final part. Definitely not what you want. Moving into Section 4, pushing materials to failure. So, to truly understand a material's limits, sometimes we have to act like forensic pathologists and perform a sort of industrial autopsy. Destructive testing deliberately pushes a sample piece of material under immense stress until it literally snaps, shatters, or deforms. That finds its absolute baseline limits. Non-destructive testing then takes that baseline knowledge and uses it to search for flaws in real-world parts while keeping them perfectly intact. Let's step over to our evidence board and see how this builds. Take the tensile fracture, for example. This piece of metal was put into a machine and deliberately pulled apart until it broke, showing us exactly how much tension it can withstand. Then, compare that to fractures caused by impact or fatigue. This shows you exactly what it looks like when a material simply loses its long-term battle against cyclic, everyday stresses. One of the most common ways to test a material's resistance to plastic deformation is hardness testing.
But an inspector can't just walk up and test the part right away. They have to meticulously prepare the surface. I'm talking about stripping away any grease, dirt, rust, paint, or coatings. Only after all that can they apply a specific compressive force, using standardized methods like Burnell or Rockwell, to get a genuinely accurate reading of the metal's hardness.
And finally, Section 5, choosing your NDT weapon.
Armed with a deep understanding of atomic structures and material limits, our industrial detective is ready to select their weapon. But an inspector doesn't just guess, right? They rely on a highly precise checklist. They have to perfectly match the physical properties of the part, whether it's ferromagnetic or non-magnetic, thick or thin, with the suspected size of the defect. Plus, they have to make sure the test medium won't damage the part, all while strictly adhering to complex code requirements. It's quite the balancing act. Let's look at a few examples of these weapons in action. Radiographic testing, which is essentially industrial X-rays, is absolutely perfect for finding deep, subsurface defects like those hidden hot tears we talked about earlier. Magnetic particle inspection? That's used for finding surface cracks on parts that can actually be magnetized. And then there's X-ray fluorescence, a highly specialized tool. Technicians use these handheld radiation guns to perform positive material identification, literally analyzing the exact percentage of elements inside a material to ensure it is exactly what it claims to be. As we wrap up this explainer, we've uncovered a totally hidden world of industrial detectives, shrinkage cavities, and handheld radiation guns. So I'll leave you with this thought. How does knowing that all of this is happening behind the scenes change your perspective on the planes, bridges, and machines you trust your life with every single day? It certainly makes you appreciate the invisible science keeping our modern world intact. Thanks so much for joining me to explore this fascinating topic.